Let's do an example of a problem involving friction. I'm going to base my example off of problem 3 from the free body diagram Newton's second law worksheet that we did last week. So here's the scenario. Again, we're pulling a box across a floor. With a horizontal rope. So just like problem 3, except this time, we'll consider the friction between the box and the floor. So we had a 120 kilogram box. We were pulling with 350 newtons of force, so that tension force in the rope is 350. And now there's kinetic friction, stickiness between the box and the ground. And we'll say that that kinetic friction has a value of 0.2. There's no units with the coefficient of friction. So a free body diagram for this problem has our standard horizontal, vertical coordinate system, our object of interest at the origin. There's the gravity force of the Earth pulling down on the box. There's the normal force of the floor pushing up on the box. There's our tension force from the rope on the box. And now there's friction. And remember that friction always opposes the direction of motion. So if we're pulling the box to the right, the friction force points to the left in the negative x direction. So that's the friction force between the floor and the box. Those are the two objects that are in contact, that are being sticky together. Now to analyze this problem, we need to start with the y direction. That's so we can calculate the normal force, which is needed to figure out the magnitude of the friction force. So in the y direction, our analysis is exactly the same as it was for problem 3. There's zero acceleration in y because the box isn't moving up or down. We have normal force in the positive y direction, gravity in the negative y direction. So that means that N equals W. And on the surface of the Earth, we know that W, gravity force, equals M times G. Now, in the x direction, here's where things get interesting. This is our new physics we're learning. We have the tension in positive x, and opposing that is the friction force pointing negative x to the left. Now, for that magnitude of friction force, we can substitute the equation we just learned. Friction force equals mu times N, coefficient of friction times normal force. And that's why we did the y direction first, because now we know that for this problem, N has a value of mg. So we'll do another substitution. And with one step of algebra, we can solve for the acceleration. And when you put in these numbers, mass 120 kilograms, tension 350 newtons, coefficient of kinetic friction 0.2, you find that the acceleration equals 0.96 meters per second squared. Now earlier when we solved problem 3 without friction, we found that the acceleration was 2.92 meters per second squared. So introducing friction into the problem between the box and the floor decreases the acceleration value quite a bit, which makes sense because when there's a lot of friction between two surfaces, it's harder to move them.